Swayam Prabha. Digital India. Educated India.
Welcome to the 36th lecture of the open course on diffusion in multi-component solids. In this lecture, I have illustrated the determination of correlation factor in FCC crystal for diffusion of an atom by vacancy mechanism. I have followed the 3 frequency model of Lydiard and Leclerc for this. Last class we derived the expression for correlation factor for a cubic material. Today we will try to apply the expression to evaluate correlation factor in an FCC lattice, particularly for the diffusion of a substitutional atom by vacancy mechanism. So, we got the expression for correlation factor as F is equal to 1 plus C over 1 minus C, where C is nothing but the average of cos theta of successive jumps for all the atoms. Now, let us try to evaluate this for FCC. In order to look into the jumps of a tagged atom in FCC, let us try to draw the FCC lattice in a little bit different way, just because it is more convenient through our perspective. So, let us consider the stacking of 100 plane of FCC. So, this is one plane, the other one we can draw is here, and one on the right side of this we will have to extend it, we have to draw the second cube here. And let us consider this cube here, so if we draw this separately, you get the same FCC lattice, but now we are putting atoms on the centers of all the edges and one atom at the body center of this cube. Now, why this is more convenient for us? Because if we consider this jump vector, let us call A x, then we can divide the atoms in different classes, the atoms in each class making the same angle with the jump vector A x. So, for example, one class contains only one atom A and it makes an angle of 180 degree with A x. The other class contains 4 atoms of type B and they make an angle of 120 degree with A x. Then we have type C which make angle 90 degree, type D making an angle of 60 degree, and type E making an angle of 0 degree. So, now let us consider the first jump of our tagged atom A tagged atom is the atom that we are tracking. Remember, we derived these expressions for mean square displacement for a large number of atoms. So, when we are tracking an atom and its jump, we have to we are calling it a tagged atom. So, the first jump of the tagged atom is, let us say, from A to X. So, now our tagged atom is at position X and the vacancy has gone to position A. So, let us say ith jump is from A to X. So, the I plus 1th jump of tagged atom, let us call it X. Now, it may be either back to A, in which case cos theta I plus 1 or let us call it cos theta A would be minus 1, or it can be onto one of the 4 B sides, for which cos theta B would be minus half, and cos theta B would be minus half, or it can be onto one of the 2 C sides, the C sides here, and they are making 90-degree angle. So, the cos theta for that would be 0, or it can be onto one of the 4 D sides. So, cos theta D would be half, because any of the jump vector x d is making an angle of 60 degree with a x, or it can be straight onto site E, for which cos theta would be 1. So, if we want to evaluate the average of cos theta I plus 1, we can write it as number of x atoms that make a jump onto A times cos theta of A plus number of x atoms that make jump onto side B times cos theta of B, and there are 4 such sides. So, we have to multiply by 4 plus number of x atoms which make jump onto side C times cos theta C, and there are 2 such sides of type C, times number of x atoms which make its I plus first jump to a site of type D times cos theta D, and there are 4 sides of type D plus n x E cos theta E, and there is only one side of the type E, divided by the total number of atoms. Remember, when we evaluate the average of cos theta I plus 1 and we have a large number of atoms, so we are tracking each of the x atom for its I and I plus first jump, evaluate the cos theta and take the average of it, right. So, we need the number of each type of jumps that the x makes, those we call as n x a, n x b and n x c and so on. If we look at this, n a x divided by n total, that is nothing but the fraction of total number of atoms which make the jump onto a site of type A, and this is nothing but the probability that the atom x will make its second jump back to A. So, let us denote it as P x A. So, this will be P x A, and cos theta A is minus 1. So, this is simply minus P x A. Similarly, Pxb is the probability that the atom X makes its I plus first jump to a site of the type B. So, this will be Pxb, and cos theta b we know is minus half, and there are 4 such sites. So, this would be minus 2 Pxb plus Pxc is the probability that X atom makes the I plus first jump to one of the C sites, and there are 2 such sites, but cos theta c is 0. Similarly, we can write for Pxd and Pxe, cos theta for d is half. So, this will be 2 Pxd plus Pxe. So, now we need to find the probability Pxs. Let us denote this Pxa, Pxb, Pxc in general by Pxs. This is the probability that the tagged atom X makes its I plus first jump to a site S. Now, what is this probability Pxs? If the atom X here has to make a jump onto any of the sites, let us say onto site B for example, then the vacancy has to be on site B, and we are considering the correlation effect. Right? When we are considering random walk, the summation of cos theta was 0. So, the only contribution to the summation of cos theta is from the correlated jumps. So, we are considering only correlated jumps. That means, we are considering the exchanges of atom X with the same vacancy. In our case, the vacancy is now at position A. This vacancy itself can make n number of jumps and come back to any of the nearest neighbor of X before the X has already exchanged second time. And then if the same vacancy exchange with this X, it is a correlated jump, because the X is exchanging successively with the same vacancy. If the X exchanges with a different vacancy before this vacancy at A comes back to one of the nearest neighbor sites, then the correlation effect is lost. We say that vacancy is lost, and the second jump of X was again a random jump, because a fresh vacancy has arrived randomly and it has already exchanged with the fresh vacancy. So, we need to only consider the exchanges of X with the same vacancy. Since the activation energy for the diffusion of a vacancy is much lower, the vacancy itself would make a large number of jumps before the X again exchanges with it. So, we need to find the probability that after making n jumps, the vacancy at A comes back to any one of this A, B, C, D and E type of sites. Okay. So, now Pxb for example is the probability that the atom X on its I plus first jump exchanges with the same vacancy which had arrived at B. So, Pxb is nothing but the probability that the vacancy after n minus 1 jumps of its own has arrived at site B times the probability that on its nth jump the vacancy exchanges with X. So, we can write Pxs as probability that the vacancy comes back to S after itself making n jumps times the probability that the vacancy exchanges with X. So, let us denote this first probability as Pn of S and the second probability by F1. We know Pxs is equal to Pns times F1. So, now we need to define the exchange frequency of the vacancy in order to get the probability of the vacancy that it exchanges with X. If you come back to this lattice, here the vacancy at A can either exchange with X itself, or it can exchange with one of these 4 B atoms which are also the nearest neighbor of X, or it can exchange with other solvent atoms which are not the nearest neighbor of X. So, we can define at least 3 different types of frequencies when the atom X is a different type of atom or when it is an impurity, because the frequency of exchange with the impurity atom is not same as the frequency of exchange of the vacancy with a solvent atom. Again, the frequency of exchange with solvent atoms may not be the same for 2 different cases. One, with the solvent atom which is seated at one of the B sites, because these B sites are also the nearest neighbor of X and there may be an impurity solvent atom binding. So, the frequency of exchange of the solvent atom at B is not same as the frequency of exchange with other solvent atoms which are not nearest neighbor of X. So, we define 3 types of frequencies here. First, we call omega 2, this is the frequency of exchange of vacancy impurity atom X. Omega 1 is the frequency of exchange of vacancy with a solvent atom that is also a nearest neighbor of X, and the third frequency we denote as K1, and this is the frequency of exchange of the vacancy with a solvent atom that is not a nearest neighbor of X. So, with this F1, which is the probability that the vacancy exchanges with X, would be omega 2 over, now if we go back to this lattice, there is only one atom with which vacancy can make an omega 2 type of jump. There are 4 sites onto which the vacancy can make an omega 1 type of jump, and the remaining 7 sites which are nearest neighbor of the vacancy are the ones onto which the vacancy can make a K1 type of jump. So, F1 can be expressed as omega 2 over omega 2 plus 4 types of omega 1 jump plus 7 types of K1 jumps. Similarly, F2 can be expressed as omega 1 divided by omega 2 plus 4 omega 1 plus 7 K1. This is the probability that the vacancy exchanges with a solvent atom which is also a nearest neighbor of X, and let us call F3 as the probability that the vacancy exchanges with a solvent atom which is not a nearest neighbor of X. So, then that would be K1 over omega 2 plus 4 omega 1 plus 7 k1, and so we can get f1 plus 4 f2 plus 7 f3 should be equal to 1. Now, once we define this, let us come back to evaluation of the second factor here, that is P&S. P&S is again the probability that the vacancy comes back to S after itself making n jumps. To get the value of P(n) of S, we can write this as the probability that the vacancy after making n minus 1 jump comes to a site which is nearest neighbor of S times the probability that the vacancy on its nth jump exchanges with the atom on S. So, this is probability we know the second part, the probability that the vacancy exchanges with the atom at S would be an, so this jump would be an omega 1 type of jump, because this is a solvent atom which is nearest neighbor to atom X. So, the probability of this, which we have defined here as F2, and the first probability we can write it as Pn minus 1 S times F2. So, Pn minus 1 S is the probability that the vacancy after making n minus 1 jumps arrives at a site S. Now, to proceed further, we will make an assumption that any vacancy which makes a K1 type of jump is lost permanently, which means if the vacancy makes a K1 type of jump, then we are not considering it anymore for the correlation. In other words, we are assuming that if a vacancy makes a K1 type of jump, then the probability that it will arrive back on one of the nearest neighbor sites of X would be much less than the probability that a fresh vacancy would randomly arrive at the nearest neighbor of X. Because of this assumption, we will have to only consider the jumps of the vacancy which are on the nearest neighbor of X. So, we need to only consider the omega 1 type of jumps of the vacancy before the omega 2 type of jumps occurs. If the vacancy makes a K1 type of jump, then the correlation ends there. The next vacancy which comes near to X is a random vacancy. In order to visualize properly, let us draw this FCC cube again here. So, we need to consider only those jumps of the vacancy which are onto the nearest neighbor of x. So, if we want to evaluate Pn of A, that is the probability that the vacancy after making n jumps will arrive at site A, then it is the probability that the vacancy will after n minus 1 jumps will arrive at any one of the common nearest neighbor sites of x, and here the common nearest neighbors of A and x are 4 B type of sites. So, this would be 4 times P n minus 1 B times F2. Similarly, if we consider Pn of B, if we consider any B atom here, the nearest neighbor of B and X, if we find they contain one A site, then one B type of site here, then one C sites and one D site. So, this would be Pn minus 1 of A plus Pn minus 1 of B plus Pn minus 1 of C plus Pn minus 1 of D times F2. Similarly, for C, if we consider any C atom, the common nearest neighbor between C and X are, we have 2 B atoms and 2 D atoms here. So, this should be 2 times P n minus 1 of B plus 2 times P n minus 1 of D times F2. Pn of D would be, if we consider any D atom, its nearest neighbors are, the common nearest neighbor are B, then C, D and E. So, we have Pn minus 1 of B plus Pn minus 1 of C plus Pn minus 1 of D plus Pn minus 1 of E, and for E atom, if we find the common nearest neighbor of E and X, they are all 4 D types of sites. So, this would be 4 times Pn minus 1 of D times F2. There should be an F2 factor here. So, if we write this in the form of a matrix, we will see Pn of A, Pn of B, Pn of C, Pn of D, Pn of E should be equal to the second column metric. We have Pn minus 1 of A, Pn minus 1 of B, Pn minus 1 of C, Pn minus 1 of D, Pn minus 1 of E, and there would be a 5 by 5 matrix here, which we can write as 0, 4, 0, 0, 0, then be 1, 1, 1, 1, 1, 0, there should be 2 and 2, so 0, 2, 0, 2, 0, then 1 in B, C, D, E, there should be 0, 1, 1, 1, 1, and 4 times Pn1 of E, so this should be 0, 0, 0, 4, 0. So, if we call the matrix on left hand side as Pn, this 5 by 5 and there should be a factor of F2, and if we call F2 times this square matrix as Q, and the second column matrix here as Pn minus 1. So, Q here is 0 4 0 0 0 1 1 1 1 0 0 2 0 2 0 0 1 1 1 1 0 0 4 0 times F2. With the similar logic, we can express Pn minus 1 as Q times Pn minus 2. So, we can write this as Q square Pn minus 2. This should be Q cube Pn minus 3, and if we keep writing this, we can write Pn is equal to Q to the power n times P0, where P0 is the probability matrix that the vacancy will be at the site S after making 0 jump. Now, after making 0 jump means we are considering the same situation where we are, and we know after the first jump of X, the vacancy is at A. So, the probability that there would be a vacancy after the vacancy had made 0 jump is 1 for site A and will be 0 for all other sites. So, we can write this matrix P0 as simply 1 0 0 0 0. This is because P0 of A we know is 1, whereas P0 of all other sites is 0. P0 of S is equal to 0 for S is equal to B, C, D and E. Now, let us try to work on it further. So, if we substitute back into the expression for C here, so we substitute for PAX, PBX, PCX, PDX and PEX in terms of Pn of A times F1, Pn of B times F1 and so on, we will get C equal to minus Pn of A minus 2 times Pn of B plus 0 times Pn of C plus 2 times Pn of D plus Pn of E times, we have this factor F1 here, and remember this n may be different because some vacancies may just make 2 jumps and come back, some vacancies will make 10 jumps and come back, some vacancies will make 1000 jumps and come back. So, n has to vary from 0 to infinity. So, we take this as a summation. So, n equal to 0 to infinity. Again, if we write this in the matrix form, we will get there is a factor of F1 times minus 1 minus 2 0 2 1 times the matrix of Pn of A, Pn of B, Pn of C and so on. It is nothing but the matrix Pn. Now, let us denote this as matrix M. So, we have C is equal to summation of M times Pn, and we know Pn can be expressed as Q to the power n times P0. So, this should be equal to summation of M times Q to the power n times P0. So, let us try to evaluate the value of M times Q to the power n. So, let us first try to evaluate the value of M times Q. We know M is equal to F1 times minus 1 minus 2 0 2 1 and Q is nothing but 0 4 0 0 0 0 4 0 0 0 1 1 1 1 0 0 2 0 2 0 0 1 1 1 1 0 0 0 4 0 times F2. So, this should be equal to F2 times F1 times, if we make this multiplication of the two matrices, minus 1 0, minus 2 0 0 0. So, this should be minus 2 minus 4 0 4 2. This we can write as 2 times F2 times F1 minus 1 minus 2 0 2 1, and again this matrix is nothing but what we defined as matrix M. So, we get M times Q is equal to 2 F2 times M. So, M times Q square we can write as M times Q, that should be equal to 2 F2 times M times Q. So, this should be 2 F2 square times M, and so on. So, if we write M times Q to power n, that should be equal to 2 F2 to the power n times M. And if we substitute back in the expression for C, we get C is equal to sigma n equal to 0 to infinity 2 F2 to the power n times M times P0. Again, if we evaluate M times P0, that should be equal to F1 times minus 1 minus 2 0 2 1, and P0 is nothing but 1 0 0 0 0. This should be equal to minus F1, and so C becomes minus F1 times 2 F2 to the power n. N varies from 0 to infinity, and this summation we can write approximately as 1 over 1 minus 2 F2. And if we substitute for F1 and F2 the way we defined this F1 and F2, F1 is omega 2 over omega 2 plus 4 omega 1 plus 7 K1, and F2 is omega 1 over omega 2 plus 4 omega 1 plus 7 K1. If we substitute, we get C, which is nothing but cos of theta I plus 1, the average over all atoms, should be equal to minus omega 2 divided by omega 2 plus 2 omega 1 plus 7 K1. And if we substitute in the expression for correlation factor, which we know F is equal to 1 plus C over 1 minus C, then we get expression for correlation factor in FCC for the diffusion of substitutional atom by vacancy mechanism as 2 omega 1 plus 7 K1 divided by 2 omega 2 plus 2 omega 1 plus 7 K1 for substitutional atom diffusion by vacancy mechanism in FCC. Now, for self diffusion, this expression can be simplified, because for self diffusion there is no binding involved between the impurity and atom, and so all the jump frequencies of the vacancy should be same, which means for self diffusion omega 1 equal to omega 2 equal to k1, and so if we substitute for this we get the value of f to be 0.818, which is very close to the most accurate determination of correlation factor in FCC, which is 0.78145. Now, there is a difference between the most accurately determined value and the value that we determined here, and this difference is because our simplistic assumption. We assumed that any vacancy that made a K1 type of jump is permanently lost. We did not consider that vacancy in the correlation effect if it made a K1 type of jump, but in reality the vacancy can go onto the second coordination shell of the tagged atom and still come back. Similarly, it can go into the third coordination shell and come back from there, and so on. So, since we ignored those jumps, we get a difference, a little bit difference here, but still we could roughly estimate the correlation factor for FCC even with this simplistic assumption. So, this was for FCC. We will also see how we can estimate the correlation factor for other cubic structure like BCC or diamond cubic. That would be in the next class. Thank you.